Howdy! Welcome to Rails DB Migrate, Even Safer, aka Safe Database Migrations 2, Electric Boogaloo. Today, we're going to be talking about how to make schema changes to your large relational database without taking down your Rails app, causing any outages or any performance impacts for your customers. Before that, though, a little bit of background about myself. My name is Matt Duszynski. You can find me online on Twitter at bsdzunk, on GitHub as dzunk, and I have a website, which is a domain hack of my own name, but it doesn't have much content on it right now. Perhaps that'll be different by the time you watch this video. A man can only dream. I currently work at Weedmaps, possibly the greenest tech company around these days. And I'm originally from Houston, Texas, although I did manage to escape the city before all of the sports teams that I know, love, and grew up watching wound up burning in a tire fire. But back to the topic at hand. Today we're going to be talking about some more advanced changes that you may find yourself needing to make to your database a few years down the road after you've accumulated a lot of data, your Rails app has grown, become successful, had a lot of new features and functionality added to it, and possibly accumulated a bit of technical debt. Specifically, the 5 things we're going to talk about are adding and removing columns safely, changing the type of a column, adding constraints to existing columns, and finally, we'll end with a case study of replacing an entire table while the application is running. Before we get into the meat and potatoes of the talk, though, a little bit of housekeeping. Going into this, I hope you know by the description that it's primarily focused on relational databases. If you came here and you use MongoDB, you might have a bad time. I'll also mention that we use Postgres as our primary data store at Weedmaps, so that's what I have the most experience with, and most of this talk is going to be using Postgres-specific terminology. That doesn't mean that the concepts don't transfer. That just means that if you're out there and you use MySQL, you might have to do a little bit of extra work. And finally, this talk does build on top of some concepts that I went over in a previous talk at RailsConf 2019 called Rails DB Migrate Safely. If you haven't seen it, or you're not familiar with these concepts or why these migrations might be dangerous at scale, I encourage you to pause the video and go take a look at the original talk, as it's going to go over some basics that we don't really go into depth here in this talk. The link may be in the description, it may be somewhere on your screen right now, it may be available in the conference Discord, it may be delivered to your house directly via carrier pigeon. But I will make sure that you get a link to that talk if you so choose to watch it. We can take a moment now and reminisce about the bygone era of 2019 and a time when we could see people in person. Good times, good times. The 3 main concepts that I covered in the original talk are locks, transactions, and concurrency. In order to understand why these migrations are dangerous and why you need to take special care when executing them, you need to know about the ACID properties of a database transaction, atomicity, consistency, isolation, and durability, and how your relational database engine uses locks to guarantee those properties across multiple connections and multiple operations, particularly with respect to migrations when schema changes are happening. There are different lock modes ranging from access share, which allows any other operation to access the row or table in question, up to access exclusive, which doesn't allow any other connection to perform any operation, including reads on the table in question. For those MySQL folks out there, those range from a select for share to a lock tables write. Access share and access exclusive are the Postgres terms. And there are other more granular locking modes as well, but they're not super relevant, although we will talk about one in particular later on this talk. Just know that they exist, and how they control access across the spectrum. And most importantly, you need to understand why these migrations can be dangerous. Any performance impact, even if temporary, in a high-throughput system can have a cascade effect that eventually takes down the entire application. If your database winds up sitting around thinking and waiting for a while, it's not going to be able to answer queries from your Rails apps that are going to have to sit around and wait for the database in order to serve their requests. This can wind up with a bottleneck of requests waiting to be served and eventually a complete denial of service. With that background out of the way, let's start with our first subject, removing a column. As an aside, and as a little bonus, we're going to cover both of the hardest problems in computer science in this talk, cache invalidation and naming things. So for this first example, we're going to go ahead and remove the name column from our users table. Perhaps we replaced it with split fields like family name and given name, or perhaps we decided that being robots, we would like to identify our users only by number. That makes for a really personable email, doesn't it? However, if you run this migration as is, you might see something like this happen in your error tracker. So what's going on here? Well, as we all know, a lot of the magic associated with Rails comes from its ORM, active record. When you boot your Rails application, active record is going to go query the database and get the current state of the schema for all relevant tables, which is how it knows what attributes are on your model, what types they are, what the default values are, and how to instantiate all of the magic metaprogramming in the background so your active record models work as you expect when you create them, update them, etc. Underneath that active record ORM layer, though, it's ultimately building raw SQL queries to perform the actual database operations. So not only do the models get instantiated with attributes based on the schema, but it also controls how the insert and update statements are built when you make changes to them. When removing a column, the column can be removed from the database, but is still present in that schema that was loaded at boot because Active Record doesn't know to reload it when you make the migration. So those insert and update queries hold on to a reference to a column that no longer exists. Fortunately, this is quite a simple problem to solve. Instead of just removing the column, we first define it as an ignored column on the model using this built-in ignored column setting. Here we're going to ignore the name column. Then we're going to deploy that change to production, and then we can safely remove the column as we saw earlier. Before we go on, I want to highlight the middle of this slide. It's imperative that you do not forget to deploy these to production separately. Most of the changes that we're going to talk about today, including this one, require a sequence of deploys to happen in a specific order. Each one needs to go out and be rolled out to 100% in your production environment to ensure that no old code is running that expects an old column, has an old version of the schema, has old application code that depends on a column that's changing, any number of things that could happen. I'm not going to be calling out each deploy specifically because that's going to be highly variable depending on your application. Are you multi-region? Any number of things. Are you running in Kubernetes like all the hotshots are nowadays? I don't know. But suffice it to say that each step that we talk about when making these migrations safely likely will require a separate deploy to production, and they're not all going to be highlighted. So, don't forget that part. And don't forget to ignore columns before you remove them. Another note when ignoring columns concerns. In a large application with a lot of developers and a lot of modules, you might find yourself needing to remove 2 columns at the same time. Building on top of our name example, here the auth team is also going to remove an old password hash from the user model. So in addition to the name column being removed from the user, we also have the old password hash column being removed from the user via the authorizable concern. However, these settings do not stack. Only the last line executed when setting ignored columns is going to take effect at runtime. So, because authorizable is included first and then ignored columns is subsequently set in the model itself, only the name column can be safely removed. If you try to remove the old password hash column, you'll receive those lovely active record statement invalid errors that we saw earlier. And I assure you that much of the knowledge in this talk has been earned through the School of Hard Knocks. So, as a matter of avoiding the issue entirely, I encourage you to only ignore columns on the model itself. This same problem can happen if you have a class hierarchy with abstract classes in it, and you have ignored column definitions at multiple levels in that hierarchy. They can conflict and step on each other, and you'll find that you haven't ignored all of the columns that you thought you did. So it's best to keep your definitions on the concrete model that refers to the table. Don't put them in concerns, and don't put them in parent classes in the inheritance tree either. So I admit that we're doing things a little bit backwards, but now that we've figured out how to remove a column safely, let's talk about adding a column, prepared statements, and how these two things can conflict. Using the active boolean on our users table, which is an example taken from my previous talk, we're going to go ahead and run the initial migration to add the column. And if you run it as it's written on the screen right now, you'll find a lot of these errors in your error tracker again. So what's happening here is an internal feature of your database driver and database engine called the prepared statement cache. Commonly used or frequently used queries, rather than being compiled and generated over and over again each time they're issued by the application, are pre-compiled, so to speak, and stored as prepared statements in the database engine itself, which allows the app to just hold on to a reference to the previously generated and executed statement. At a very, very high level, what that looks like is this. The first time you issue a query, Rails builds the actual SQL and sends that over to your relational database. It asks it to remember it as a particular statement with a name or an identifier, in this example 1, 2, 3. And then the second time your application issues that same query, instead of building the SQL and sending that over as a string, it's just going to ask your database, hey, remember that statement that we talked about earlier? Go ahead and execute that for me again. So this can become dangerous because prepared statements need consistent inputs and outputs in order to remain valid and usable by the application. When you're changing columns, in this case adding one, the results that your statement returns can change, which would make it invalid. And when you're inside a transaction, operations can't be independently retried. So the prepared statement that was executed can't be retried by the database or the application, so it raises out one of those lovely prepared statement cache expired errors that we saw earlier. Now, Rails will handle the internal cleanup of the prepared statement cache when it sees this error, but it's not aware of your business logic, and so it's not going to automatically retry anything that was happening as part of that request or part of that background job. So what this usually results in is a spike of 500 errors served while that migration runs and until the prepared statement cache is cleared out, or a spike of failed background jobs if the transactions happen to be occurring async. Now, there's not a huge amount of discussion about this out there, but most of the advice you can find falls into a few distinct categories. Number one, just disable the whole thing. And that's fair enough. You don't really need the prepared statement cache, and if it's causing you more harm than good, go ahead and turn it off. There's a setting for that. Number two, if you would like to continue running with it, you can manually rescue this error in your business logic and retry the transaction or reperform whatever was happening at that time. However, that's a very manual process and error-prone and requires a lot of work from your developers. There are also some less useful pieces of advice out there as well. However, I'm bringing to you today a clever workaround for this problem using the internals of Rails. Specifically, that ignored columns setting that we talked about earlier. It turns out that when you provide any value to ignored columns, including a fake value, as you can see in this example, it will avoid the prepared statement cache errors that occur in select statements inside a transaction. And the reason why is that because instead of this little wildcard in the statement, which is what automatically picks up the new columns when you run that migration and it gets added, setting a value for ignored columns will compel Active Record to project all the column names explicitly into the statement. And because all of the column names are included in the statement, when that statement is cached, the new column added will not be picked up in the result set, so the results will remain consistent, so the cache is still valid, and so you don't get any errors. Now, I know what you're saying. Wow, what a clever workaround. Well, fortunately, I and some of the wonderful folks that work on Rails agree, and hopefully coming soon to a Rails near you, Rails 7 most likely, is a setting to actually control this explicitly instead of relying on the implicit behavior, so to speak, of the ignored column setting. So we've added some columns, we've removed some columns, and now let's talk about adding constraints to the data that lives within them. Specifically, we're going to add a not null constraint to the user's active column that we just added in the previous example. If you run this migration as written, however, you might see something like this on your APM charts, a huge spike of latency that quickly resolves itself after the migration completes. The reason being is those locks that we discussed earlier. When you're adding a constraint to a table, by default, Postgres is going to validate that constraint against all existing rows. And in order to do that, it's going to obtain the most restrictive lock possible, an access-exclusive lock, to prevent any inserts or updates from adding data that could potentially be invalid while it's checking all of the rows in the table. And, of course, an access-exclusive lock on a high-traffic table in your system can have far-reaching performance impacts. In this case, the users table is a particularly egregious example because it's very likely that most requests depend on some sort of current user method, which implicitly depends on the user's table in order to look that person up. So a migration that obtains an access-exclusive lock on an important table or a high-traffic table or a widely used table can have performance impacts throughout the entire system. Now, there are two ways to avoid this, or I should say there's one way with two DSLs. The first thing we're going to look at is the raw SQL version, and the second thing we're going to look at is the new Active Record goodness. The raw SQL version here is adding a check constraint to the table. If you're not familiar with the syntax of a check constraint, It's basically a name and a SQL clause, like you would find in a where clause, that gets enforced when rows are inserted or updated on the table in question. Functionally, a check for column is not null is identical to defining that column is not null in the schema. The most important piece here is that the check constraint is added, not valid. This means that invalid records can continue to exist in the table, so Postgres doesn't need to obtain that highly restrictive lock and validate all of the rows that currently exist. We do want to validate those rows, but we're going to do so in a separate operation. The validate constraint operation obtains a share update exclusive lock, which is far less restrictive than an access exclusive. It allows reads and writes to continue on the table, and basically only conflicts with other schema changes, which hopefully you're not performing multiple schema changes concurrently. Now, I mentioned earlier that there's some active record goodness for performing exactly this. And if you've noticed the title of these slides, or perhaps this version number in the migration, you'll see that the raw SQL version is usable in Rails 6 and below by direct execution. However, Rails 6.1 added a new DSL for handling this called add check constraint. And it operates in exactly the same way. It's just a friendlier Ruby version of the statement that we were seeing earlier. And you can see here that it has the same pieces: the table name, the constraint clause, the name of the constraint, and again, importantly, the instruction to not validate it when adding it to the table. And the DSL for validating it is very similar, called validate check constraint. Another nice feature of the Rails 6.1 DSL is that check constraints are included in the schema dump now. So it's much easier to keep multiple environments and development environments in sync and up to date. The bottom line is you can use check constraints rather than column constraints to enforce data integrity in your database. If you're on a fairly modern version of Postgres, you can actually go back after the check constraint has been added and validated and add the more common not null column constraint and remove the check constraint. With the check constraint in place, it's functionally identical to a column constraint, so Postgres doesn't need to obtain a restrictive lock and revalidate all those rows. You can just convert the constraint basically into a column constraint and then drop the check constraint afterwards. It's not a huge deal, but it's worth noting that there is a small performance impact to check constraints on the level of about 1% reduction in read performance. So if you have a large table with a lot of check constraints, it can add up. So if you have the opportunity to convert them into a column constraint which doesn't suffer from that performance regression, then it might be appropriate to do so. All right. I promised we were going to cover both hard things in computer science, and we're on number 2, naming things. More relevant to the topic of this talk, we're going to talk about how to change the type of a column. Now, this section is a bit of a misnomer because you can't. It's not possible to change the type of a column safely while your application is running. You'll either have the old version of the application expecting the old version of the column and be okay with it, while your new version is dazed and confused, or vice versa. The migration runs and the new version of the application expects the new column type, while the old version sits there and says, "What?" Fortunately, you can effect this change with a simple 6-step process, each step requiring its own commit and a corresponding deploy to production. First, add a completely brand new column with the correct type. Then, you want to add a mechanism to keep the new column and the old column in sync as your application makes changes to the model in question. Third, run a backfill task to update all the existing records with a correct value in the new column that you added in the first step. Then, add indexes and constraints to the new column based on what you have configured for the old column, or any new constraints or indexes that you may need to add. Then, point the model at the new column and ignore the old column using the ignored column setting. And then finally, you can drop the old column and you've successfully changed the type of your data. For this example, we're going to use a price field. And some developer in the days of yore committed one of the cardinal sins of database engineering and stored prices as a float. And we want to convert that into a decimal. If you so chose, you could convert it into an integer, store the value in cents. There are alternatives. Just don't leave it as a float, please. And since we need to add a new column and have both of them coexist, we are going to name our new column new price. So let's start by adding the new price column. Once the column has been added, we need a mechanism to keep its value in sync with the existing price column. Now, there are two main ways to approach this. You can use triggers at the database level or callbacks at the application level. The triggers would look something like this. You create a trigger on the table. After inserting or updating records, you execute a stored procedure to set the value of the new column based on the value of the old column. The benefit of approaching it with a trigger is that the logic is decoupled from the application and doesn't depend on any sort of external system in order to keep the database in a consistent state. You can much more confidently add those constraints in the later step, knowing that your database is internally consistent and doesn't depend on the application to make the correct updates to both columns. You can also keep the data in sync after ignoring the old column and potentially have an easier rollback path. However, if you don't extensively use triggers in your application, you might not have a good way to manage this because they're not something that's included in the schema dump by default. So it can be difficult to coordinate across environments or version control a database trigger for a one-off operation like this. The second option is to use callbacks within your active record model to set the value before saving the record. You also likely want to update the setter for the attribute itself to set the value, because otherwise you might wind up using an incorrect value at runtime if you access the wrong column, either the old one or the new one. The benefits of using a callback are that it's much easier to transform values because that can live right here within your business logic. You can imagine that if you were storing the new value of price in cents instead of dollars, it would be trivial to add a times 100 to these setters and callbacks and have the value transformed based on rules within Ruby and not rules stored in an opaque procedure in your database. This behavior can also be feature flagged or controlled with an environment variable and toggled on and off at runtime, which makes it safer to roll out, and if it has any sort of impact on application behavior or performance, can easily be turned off. Changes to the database triggers would require separate migrations, which can be more time-consuming to write and to deploy. But whichever mechanism works for you, the important thing is to have some sort of logic in place that keeps the old column and the new column perfectly in sync with any updates or changes made to the old column. Once that's done and future updates are synced up correctly, then you can come and update existing records. Now, there are a couple ways to approach this as well. Here we're using a rake task with a batch update of the model in question. And there are two important things to note about this rake task. Number one is it's conditional on only the records that need updating. And this is possible because of the previous step. We know that any change that takes place after that's been deployed has already been picked up. So the only thing that we need to worry about are rows that don't have a value yet because they haven't been updated by the callback or the trigger. This makes the rake task idempotent because it will only update records that haven't yet been updated. It can be safely stopped and restarted, which depending on the size of your table may be critical in order to run it off hours or over the course of several days, or whatever works best for your environment. The second part to note here is the in batches. As discussed in the previous talk, it's important to avoid updating every record inside the table in a single transaction because that will obtain extensive locks across the entire table and prevent other processes from writing to it. So you want to update your records in batches and avoid locking the entire table when making data changes or schema changes, or in this case, data backfill. And if you're using a rake task like this, you may want to consider adding a progress bar or some sort of other output to indicate that the task is running successfully. Once all of the rows have been backfilled and the continuous updating procedure is in place, then we can come in and add any constraints such as indexing, not null constraints, or anything else that you may want to add to the table in question. We're adding these afterwards instead of when the column was first added because having an index column or having constraints on a column adds overhead when adding or updating rows, and we want to avoid that overhead because of the potentially lengthy backfill process. Adding the indexing after the fact skips index validation. Adding the constraints after the fact validates the constraints in one fell swoop and can shave hours or even days off of your backfill time depending on the size of your table. Now at this point, all the preparation is complete, and I highly encourage you to sanity check these changes that you've made. The next operations are going to become destructive and irreversible, and so now is the time to ensure that your new column has correct values for all of its rows, it's being updated correctly, it performs as you expect, it's usable by the application. Anything you need to do at this point to convince yourself that everything has been done correctly, now is the time to do it. In this example, we would check that the new price value is equal to the old price value, or rather that there are no rows that have a mismatch between the new price and the old price. Once we've convinced ourselves that everything is good to go and the new column is completely accurate, up to date, and usable, it's time to do the big cutover. Here, we're going to remove the model level callbacks that we added in the earlier step and point the model at the new price column. We're using the alias attribute functionality of Active Record to tell the model that the price column is actually an alias of the new price. This maintains the public interface of your model, but backs it with the new column and all of the new data that we just filled in. In this same step, we can ignore the old price column because it's been completely replaced with new price and is no longer relevant. This prepares us for dropping the column in the next step. You'll note that with the callback method that we used here, this change will decouple the new price and the old price columns, and the old price will now become stale and outdated as time passes and changes occur to product prices. So that's why this is really the point of no return. It's of course possible to roll back from this, but it's not as simple as deploying a previous version of the application. You would need to manually rectify any data changes that happened after this change is deployed. So that's why it's very important to sanity check the new column before rolling out this change. However, once you have rolled out this change, then it's a simple matter of removing the old column and your column type change is complete, mostly. It may be good practice and a matter of database hygiene to do a little bit of additional cleanup. For example, if you don't particularly like my new price convention, you may want to perform this exact same set of steps to rename the column into price. It's worth noting at this point that while we used changing column type as an example here, this process is applicable to many otherwise dangerous schema changes. For example, renaming a column without changing its type is also covered by this process. Now, at this point you might be saying, gee Matt, this seems like a really painful and tedious way to make schema changes. And I would say, you're absolutely right, it is. The best solution is, of course, don't make these mistakes in the first place. When your application is at scale and your database grows very large, it becomes costlier and costlier to make these sort of changes. So modeling your data correctly to begin with is always going to be the best option. Speaking of painful and tedious, let's wrap things up here by looking at what it takes to replace an entire table at runtime. And to give you a little bit of backstory, I have to take you back to a small website called legalmarijuanadispensary.com. And that website listed legal marijuana dispensaries, and life was good. But as that company grew and that company changed and rebranded into Weedmaps, we started listing other types of business as well, like delivery services or doctors so patients can get their medical recommendations. After a while, we found ourselves with 3 distinct models backed by 3 distinct tables, all with substantially similar functionality and nearly identical sets of attributes. A classic use case for Rails single table inheritance. However, in order to get to that single table inheritance world, we needed to take an incredibly important domain model and change the table it was reading from at runtime, and have both of those tables kept in sync so we could make that deploy. Now, this sounds incredibly complicated, but it's really just applying the techniques of changing a column at a much larger scale. First, we create the new table with the updated schema. We're going to find a way to keep it in sync with the old table. We're going to backfill the new table with all the existing records from the old one. Add indexes and constraints to the new table after the backfill is complete in order to avoid performance considerations with the backfill. Point the model at the new table once we've sanity checked all the data. And finally, drop the old table. So, let's get things started and create our listings table. Now, most of the examples that you're going to see in this section are significantly condensed from the actual models, tables, etc., because listing is an extremely large and complicated model for us. It has a lot of business logic and a lot of properties associated with it. So most of the examples here have been shortened for brevity. Here, we're creating our listing table with only simple types, default values, and omitting any constraints or indexes that would cause performance issues with the bulk insert process. Even menu ID here, which is ultimately a reference to the menus table, is being added as a plain integer. We'll go back after the fact and add indexing, constraints, and foreign keys to that column once the table has been backfilled. For this migration, we decided to use application-level callbacks in order to keep the tables in sync. We did this for a couple reasons. Number one, the ease of feature flagging and disabling the change, but most importantly for our specific case was that the old and new models were not a one-to-one translation. So the new listings table and the old dispensaries table didn't match up exactly, and executing those changes purely through database triggers would have been very arduous to maintain. As an aside, if you do wind up needing to change out a table for whatever reason, I encourage you to resist the temptation to make a bunch of unnecessary schema changes at that time. It may seem like you're avoiding a lot of the column change process that we described earlier, but what you actually wind up doing is making the table migration a lot more difficult than it needs to be, which you generally want to avoid with a change as significant in scope as this. Within the application, we packaged all of the logic concerning updates to the new table into a single listing migration concern, which has three main parts: the callbacks that actually perform the updates, the logic for how to create or update the record based on the current state of the new table, and the attribute parsing to generate the new record correctly based on the values from the old one. With these callbacks in place, and with our old model updating the new model as changes are being made, we again come to the backfill stage, which also is the only time I had to shrink the font size in order to fit all of the code onto a single slide. Fortunately, there's only two main relevant parts inside the async job boilerplate. We have each job executing a migration for a single record, and then a batch in queuing of jobs for every single listing record in the system. This is an alternative to the rake task method we looked at earlier when adding the column, and we went with an async job here for a couple reasons. Using Sidekick batches, we get a lot of nice features like being able to see the progress in the dashboard, catching and correcting individual failures for specific listing records, and we avoid the risk of a long-running task that could potentially fail or be killed before it completed. This is especially important with the listing migration because there's no way to identify which records have or have not been updated correctly. You just have to run the task all the way through if it fails until it completes successfully. And in fact, while we were rolling this out, it was a fairly long-tail process of running, having it be 99.5% successful, and then tracking down a handful of failures associated with specific records, figuring out why they failed, and working around that particular issue, which is a lot easier with a background job that can be retried for a single record. Now that our table's backfilled and kept up to date, it's time to add those indexes, foreign keys, and other constraints that we mentioned earlier. Here, we're adding an index to our Weedmaps ID for the listing. We're adding a not null constraint to that column, unsafely, I might add, but bear with me for the sake of example. And we're safely adding a foreign key using a very similar technique to the check constraints that we added earlier. Add the key without validating it, and then subsequently validate the key in a second operation. With our table up to date and the schema constraints in place, it's time once again to sanity check your data and make sure that you've done everything correctly up to this point. Double check your schema, double check your records, spot check your records by hand, compare values from the old table to the new table, do everything you need to do in order to make sure that you've done things correctly. Because the next part is cutting over from the old table, or the legacy listing, to the new listing. And it's a bit anticlimactic, I think, because it's as simple as pointing the model at the new table. And in this case, telling it that it's now an STI model. And you would not believe how satisfying it is to have this part go off without a hitch, because the next part is finally dropping that old dispensaries table. Now, we covered a lot with this case study, and quite honestly, we glossed over a lot too. You may feel like you're being asked to draw an owl right now if you had to run out and do this yourself. And you'd probably be right. It's a really difficult and complicated process that's going to vary a lot for each application and for each individual case. And it's a delicate process as well. Here's a look at my team executing this change on our application. The important thing to remember is this: software is infinitely malleable. All the code, all the columns, and all the tables that you see were ultimately generated by a human, at least until GPT-3 takes all of our jobs. But that's neither here nor there. Taking the schema that you have and continuing to evolve it into the schema that it needs to be is very possible, whether that be adding or removing columns, adding constraints to your data, or even replacing an entire column or an entire table. Nothing's impossible, it just takes work, and it takes know-how of how to do it safely. Hey, thanks for watching. If you have any questions about what we covered in this talk, please hit me up on the conference Discord. We have a Q&A channel, Rails DB Migrate Even Safer, that I'll be in for the duration of the conference. And we have a specific Q&A slot on Thursday afternoon for you to pop in with any questions you may have. Also, follow me on Twitter, fork me on GitHub, and go out there and migrate safely.